Hi, this is Justin Chu.
And this is Kevin Sang.
Welcome to our final project demonstration for CS184. This project is an inverse kinematics solver using cyclic coordinate descent algorithms. So this first example shows two bones following a very simple line back and forth. As you can tell, our cyclic coordinate descent algorithm makes sure that the bone end effector is as close as possible to the target, and this situation actually is touching the target.
In this example, we have 4 bones instead of 2 bones, and very similar to the last example, the light bulb indicates where the path or the target in the path is, and the end effector is touching the path at all times.
In this example, we also have 4 bones, but we moved the target path farther away from the root. This causes the end effector to be not able to touch the actual target position successfully. However, because of the cyclic coordinate descent algorithm, the end effector position and target position are always going to be minimized. So even though at certain points they are the same, the end effector position and target position, at other points they are not, because the bones can't reach that point. Nevertheless, the bones still continue to try to reach that point as close as they can.
In this example, we're tracing a circle, which is a non-trivial path. This example is just to illustrate that we can create very interesting paths for our IK solver to follow. In this example, much like the last one, the radius of the circle is too long for the bones to reach, and thus it can't actually reach the target of the path, but we show that because it is, even though it's so far away, it's still tracing out a circular path.
Now we have 4 bones, once again, following an elliptical path. This path is a little bit different from circular path, mostly because of different shape, and also you can see that at certain points the bones can actually touch the path, at other points it cannot. Just to reiterate, this is because the cyclic coordinate descent algorithm, end effector, and target position are minimized.
In this example, where our IK solver is tracing out a figure 8 path, as you can see, as the end effector approaches the cross-section of the figure 8, it exhibits some very jerky movements. That's because in the cyclic coordinate descent algorithm, there are some unoptimal movements or translations when it reaches this point.
Still, even though the cyclic coordinate descent algorithm creates some unoptimal movements, it is one of the faster inverse kinematics solver algorithms out there. Here we are rotating the view so that you can see how our bones are actually 3-dimensional. These bones obviously live in 3D space, and the rotation is caused by different keyboard inputs, and we can actually rotate in different axes. Now we're rotating the opposite way. And out of the way.
In this example, the IK solver is trying to get to a path which can't be seen. In this example, we're showing you translations that our IK solver can do. In a moment, you'll see that we're zooming out so we can see the path. And right here, we're showing translations left and right and up and down. Here, we're zooming out even more. Now we're zooming in and zooming back out. And just another rotation and some more translations.
In this example, the root bones starting coordinates are not the origin, and so we actually translated the root bones starting position to not be the origin anymore. The behavior though is what you expect. It still tries to minimize this between the target position and the end effector, and it's doing so pretty successfully. This is a good example of how the bones are not the most optimal when they wrap around and are touching the end effector, but once again, it does the job.
One of the features we wanted to implement was to allow the user to define arbitrary paths that the IK solver can follow. And so in this path that we've shown here, we've actually given the IK solver a list of points for it to trace the path out of. And so in this example, we have a cube-like path for the IK solver to trace. And as you can see, the path does not lie on just simply one axis. It lives in 3D space, and the IK solver can still traverse this path in all 3 dimensions.
So this is near the end of our presentation. We'd like to thank you for watching this video, and we hope you enjoyed it as much as we enjoyed building it.
Thank you.